Somewhere in the first half of 2026, engineers at OpenAI, Google, and IBM all went quiet at almost the same time. Not because something went wrong, because something went right, faster than most of them had planned for. A handful of labs, working independently, had just solved a problem that had blocked quantum computers for 2 decades. And within weeks, the same machines that were supposed to be a decade away from mattering started showing up in earnings calls, government funding announcements, and Wall Street sell-offs. This is the story of what actually happened, what's still uncertain, and why the company that built ChatGPT suddenly has a reason to care about a technology it barely mentioned 2 years ago. Let's start with the basic problem, because you need this to understand everything else. A regular computer, the one in your phone or laptop, stores information as bits. Each bit is either a 0 or a 1, like a light switch that's either off or on. A quantum computer uses something called a qubit, and a qubit can be off, on, or a strange mix of both at the same time. Picture a coin spinning in the air versus a coin lying flat on a table. Heads or tails, that's your regular bit. The spinning coin, still deciding, still in motion, that's closer to a qubit. That in-between state lets a quantum computer explore many possible answers to a problem at once instead of checking them one by one. For certain kinds of math, that's an enormous shortcut. The catch is that spinning coin is incredibly fragile. The tiniest vibration, a stray bit of heat, even a cosmic ray passing through the chip can knock it over and ruin the calculation. For years, the industry's biggest obstacle wasn't building more qubits. It was keeping them stable long enough to trust the answer. And that fragility is exactly what changed in 2026. A research team based in Zurich published a new way of packaging qubits together, called an error correction code, that dramatically cut down how many physical qubits you need to create one reliable, logical qubit, the kind of qubit stable enough to actually compute with. Instead of needing thousands of fragile qubits just to fake one dependable one, their method needed far fewer. That freed up capacity that used to be wasted purely on stability, and let more of the machine actually do useful work. Here's the part that made this a genuine turning point instead of one lab's lucky paper. Google's quantum AI team was working on the same problem from a different angle, and showed that their Willow processor could hold a stable quantum state long enough to run meaningful optimization tasks tied to AI systems. IonQ, which builds its machines using trapped ions instead of Google's superconducting approach, trading raw speed for extra stability, demonstrated similar staying power around the same time. 3 different hardware philosophies, 3 separate teams, converging on the same conclusion within months of each other. That's rare in any field of science. And it's the reason people inside the industry started calling 2026 a tipping point, rather than just another incremental headline. But convergence in a lab is one thing. What happened next is what pulled OpenAI and every other AI lab into the conversation. Because it turns out the exact math problems that trip up classical computers, the ones involving searching huge tangled spaces of possibilities, look a lot like the optimization problems buried inside training large AI models. Quantum computers are built to be good at exactly that kind of search. And once quantum machines got stable enough to actually attempt it, the 2 industries that used to live in separate worlds suddenly had a reason to start talking to each other. IBM didn't stay quiet either. The company has publicly stated that 2026 will be the year a quantum computer outperforms a classical computer on a specific defined problem, a milestone the field calls quantum advantage. That's a big claim, and it's worth being careful here. Quantum advantage on one narrow, cherry-picked task is not the same as quantum computers being generally better than the supercomputers running in data centers today. Think of it like a bicycle beating a car in a race, but only on a single obstacle course built specifically to favor the bicycle. That's still a real win. It just doesn't mean the bicycle is about to replace the car on the highway. Quantum advantage is a meaningful step. It is not, on its own, proof that quantum computers are ready to take over AI training, or anything else running in a normal data center today. Keep that distinction in your back pocket, because it matters for what comes later. Meanwhile, IBM has laid out plans to build a machine with over 4,000 qubits by connecting 3 separate chips together, a scaling strategy that treats the problem less like building one bigger single processor and more like linking several working ones. Fujitsu and Japan's Riken Research Institute announced their own 256 qubit system, with a stated goal of reaching 1,000 qubits. Different companies, different roadmaps, all racing toward the same horizon line. And then Nvidia, the company that makes most of the chips training today's AI models, stepped directly into the middle of this story. In April 2026, Nvidia launched a family of open source AI models called Ising, designed specifically to help calibrate quantum processors and correct their errors faster and more accurately than older methods. Nvidia's own claims put the improvement at up to 2.5 times faster error correction, with roughly 3 times better accuracy compared to traditional approaches. Research institutions, including Harvard's Engineering School, Fermilab, and quantum hardware companies like IQM and Inflection signed on to use it. In other words, the company powering the AI boom just quietly built a bridge straight into the quantum boom. That's not a coincidence, that's a strategy. So where does OpenAI actually fit into all of this? And here's where we have to be honest with you, because a lot of headlines out there make it sound like OpenAI issued some dramatic warning or victory statement about quantum computing. It didn't, not in the form of one big press release. What actually happened is quieter and in some ways more interesting. OpenAI's public posture toward quantum computing has shown up in pieces, not proclamations. Sam Altman has floated the idea, in interviews, that a future model, something well beyond today's systems, proving it can solve open problems in quantum gravity, one of the deepest unsolved puzzles connecting quantum mechanics and general relativity, would be a legitimate marker of true general intelligence. David Deutsch, a physicist widely credited as a founding figure of quantum computing theory, publicly agreed that this would be a fair benchmark. That's not OpenAI reacting to a quantum computing breakthrough. That's OpenAI treating quantum physics itself as one of the hardest tests it can imagine for its own technology. Separately, OpenAI's newer reasoning models have already been credited with helping resolve an open problem in statistical learning theory, a corner of mathematics that underpins how machine learning works in the first place. And the company has been building out an initiative called OpenAI for Science, explicitly framing AI as, in their words, the next great scientific instrument, with dedicated teams working alongside researchers in physics, math, and biology. OpenAI has also joined the Department of Energy's Genesis mission, a government-backed push to speed up scientific discovery using AI across national laboratories, the same kind of institutions that run some of the country's most advanced quantum research programs. Put those pieces together and you get a company that isn't panicking about quantum computers replacing its AI models anytime soon, but is very clearly positioning itself to use AI as a tool for accelerating physics and quantum research, while treating mastery of that same physics as a long-term milestone for its own systems, not a threat to them. Compare that to a company like Rigetti, one of the pure-play quantum hardware makers. Its own CEO has publicly predicted that pairing quantum computing with AI could turn out to be a faster, more elegant route toward advanced AI systems than simply scaling today's models with more chips and more data, and he said openly that most investors haven't fully priced that idea in yet. Notice the difference in posture. The quantum hardware company is trying to convince the world that AI needs quantum computing. The leading AI lab is treating quantum physics as one more scientific frontier to conquer with the tools it already has. Both of them might end up being right. Neither of them has proven it yet. So if you were expecting OpenAI to have sounded some kind of alarm, that's not quite what's happening. But don't relax yet, because somewhere else, in a very different part of this story, there's a genuine reason for concern, and it has nothing to do with AI training speed. It has to do with your data, right now, today, sitting in a server somewhere. Security researchers have long warned about something called harvest now, decrypt later. The idea is simple and a little unsettling. A sophisticated adversary doesn't need a working quantum computer today to steal your encrypted information. They just need to copy it now, store it, and wait. Because once a quantum computer becomes powerful enough to break today's most common encryption methods, a device researchers call a cryptanalytically relevant quantum computer, all of that stored data becomes readable retroactively. Bank records, corporate secrets, government communications, personal messages, anything encrypted using older methods could, in theory, become an open book years after the fact. For a long time, estimates for when such a machine might exist clustered around 2035 or later. That number is now being pulled forward by some analysts, with a few pointing toward the early 2030s, given how fast error correction has improved. But here's the honest caveat. Experts differ sharply on this. Nobody serious in the field is claiming a certain date, and building a machine that's stable at the scale needed to actually break modern encryption is a completely different challenge from demonstrating quantum advantage on one narrow research problem. Be skeptical of anyone who gives you an exact year with total confidence. The responsible answer, right now, is that the timeline compressed somewhat in 2026, and nobody fully agrees by how much. The good news, if there is good news here, is that this threat was anticipated. The U.S. National Institute of Standards and Technology finalized a set of post-quantum cryptographic standards back in 2024, designed specifically to replace today's vulnerable encryption methods with versions that should hold up even against a future quantum computer. The tools to defend against this threat already exist. The remaining question is how fast organizations actually adopt them before the clock runs out, and that's a much bigger, messier problem than the physics itself. Think about how long it takes a large bank or a government agency to update software running on systems that were built decades ago. Encryption isn't a single switch you flip. It's woven into thousands of individual systems, apps, and protocols, many of which nobody has fully mapped out yet. Security researchers sometimes compare it to renovating a building's plumbing while people are still living inside it. You can't just shut the whole thing down and start over. Governments move slowly. Legacy systems are everywhere. And that gap between having a solution on paper and actually deploying it across every vulnerable system on Earth is where the real risk quietly lives. And it's a bigger factor in how exposed we actually are than the exact year a quantum computer becomes powerful enough to exploit it. Now, all of this technical progress didn't stay confined to research papers and government memos. It hit the stock market, and it hit hard in both directions. Quantum computing stocks had an extraordinary run heading into 2026. Companies like IonQ, Rigetti, and D-Wave posted trailing returns ranging from the hundreds of percent into the thousands, numbers that made even the AI stock boom look tame by comparison. IonQ alone reported first quarter 2026 revenue of $64.67 million, a jump of 755% compared to the year before. The company's CEO called it the strongest quarter in the company's history. A benchmark index tracking the sector, the S&P Kensho Global Quantum Computing Technologies Index, was up over 69% through the end of May 2026, more than 6 times the broader S&P 500's gain over that same stretch. Then, in May, the U.S. Department of Commerce announced over $2 billion in funding under the CHIPS and Science Act, spread across 9 quantum companies in exchange for equity stakes in each one. IBM alone was reported to be the anchor recipient of roughly $1 billion of that package. That's the government putting real money behind a bet that quantum computing is no longer purely theoretical. But speculative sectors that rise fast tend to fall fast too, and quantum stocks proved it. Later that same month, IonQ, Rigetti, D-Wave, and Quantum Computing Incorporated all dropped between 6 and 9% in a single trading session, even though none of their underlying business fundamentals had actually changed. Analysts pointed out that these 4 companies use completely different technologies: trapped ions, superconducting circuits, quantum annealing, photonics, yet the market trades them as one single basket, rising and falling together based on sentiment as much as substance. Some financial commentators have gone further, openly predicting that the quantum computing sector is running on unsustainable valuations and due for a sharper correction, pointing out that most of these companies still report minimal revenue and no profits despite trading like they've already won. Others argue the long-term case is only getting stronger as the underlying technology matures, noting that the global quantum computing market, while still small today, worth an estimated $2 billion in 2026, is projected by some industry groups to grow toward figures in the range of $16 to $19 billion by 2035. Both camps are looking at the same numbers and reaching opposite conclusions. And that split itself tells you something about how early we still are in this story. When a technology is genuinely mature, analysts tend to agree on roughly what it's worth. When they're this far apart, it usually means nobody actually knows yet, and everyone's just placing a bet. So where does that leave the actual usefulness of these machines beyond the stock ticker? A quantum computing company called Quantinuum launched a system named Helios in late 2025, which it describes as the most accurate commercial quantum computer available. Real companies are already running research on it, including JP Morgan Chase, SoftBank, Amgen, and BMW. That's not a hypothetical use case. That's institutions with real budgets deciding it's worth paying to experiment with quantum hardware today, even while everyone agrees fully practical, fault-tolerant quantum computers capable of outperforming classical machines across the board are likely still years away. And this is where the 2 threads of this story, AI and quantum computing, genuinely start to braid together instead of just running in parallel. Executives across the industry have started predicting that pairing quantum computing with AI could turn out to be a faster, more elegant path toward more capable AI systems than simply making today's AI models bigger. That's a prediction, not a settled fact, and it's one that hasn't been fully tested or proven at scale yet. Some in the investment world think that combination is still underappreciated by the market. Others think it's exactly the kind of speculative story that inflates a bubble before the technology is actually delivered. Both things can be true at once: a real scientific direction worth watching, and a narrative that's currently running ahead of the evidence. So where does that actually leave us? At the end of a year that keeps getting called a turning point before it's even finished? The honest picture is less dramatic than the headlines, and more interesting because of it. Quantum computers did not suddenly become smarter than classical supercomputers at everything, and OpenAI did not issue some emergency statement declaring an existential shift. What actually happened is quieter and, in a way, more human. Several separate teams of scientists solved a decades-old stability problem around the same time. A government decided that was worth billions of dollars of insurance. A stock market reacted the way stock markets always do, with excitement first and skepticism catching up right behind it, and one of the world's most closely watched AI companies quietly folded quantum physics into its own definition of what real intelligence might someday look like. None of that is science fiction. All of it is still unfolding. And nobody, not IBM, not Google, not OpenAI, actually knows yet which predictions from this year will look prescient in 5 years and which ones will look like 2026's version of hype. If you want to actually understand where this goes next, instead of just reacting to the next headline, that's exactly the kind of thing worth subscribing for, because we'll be tracking every real update as it lands, not the exaggerated version. What we can say with real confidence is this: the distance between a quantum computer that wins in a lab and a quantum computer that changes your daily life just got shorter than almost anyone expected 12 months ago. Whether that shorter distance turns into the next great leap in computing, or just the most expensive lesson in patience the tech industry has learned in years, is still being written by researchers in Zurich, engineers at Google, analysts on Wall Street, and yes, quietly, by the people at OpenAI who are watching this unfold just as closely as you are.